Hi everybody, welcome to our video on simplified isostatic mass balance calculations. Wow, that is a mouthful. But in previous videos, we've talked about this concept of isostasy. This is the idea that essentially the lithosphere can be thought of as floating in the mantle asthenosphere. And so as the lithosphere gets thicker or thinner, or as we pile loads like ice onto the lithosphere, it may float higher or lower within the asthenosphere, much like a boat might float higher or lower if it was loaded with cargo or unloaded. So in this video, what I want to do is tell you how to actually estimate the height of a lithospheric block, how high above the asthenosphere it's floating. This is a pretty technical video, and it's not really intended for mass consumption. It's intended for people who want to learn how to make these calculations of height. If you're just interested in the broad concepts, please see my other video on isostasy and flexure. Okay, so in this video, we'll start out with the overview and some assumptions, and then we'll talk about how to estimate the elevation of a floating block. So in this video, we're going to use a simplified version of isostasy. We're essentially going to view the lithosphere as a series of free-floating lithospheric blocks. So here they are. Here's an area of thinner lithosphere and an area of thicker lithosphere. And we're going to let each block float at some unique equilibrium that's predicted by its thickness and its density. Okay? So we're essentially going to be calculating how high one of these blocks is floating above or below this hypothetical top of the asthenosphere. So a few intuitive points before we get started on the math. One point is that blocks with the same density but different heights will still have the same percentage of the block above the top of the asthenosphere. So we see that here. This block is roughly half the thickness of this block, okay? But because they have the same density, they both have roughly 15% of their thickness floating above the top of the asthenosphere. This is exactly analogous to two icebergs, a large iceberg and a small iceberg. Because ice has the same density, both icebergs would have the same percentage floating above the top of the water. Now in contrast, if blocks have the same height but have different densities, we would predict them to have different percentages floating above the asthenosphere. So in this example, we've got a piece of dense oceanic lithosphere and a piece of lighter or more buoyant continental lithosphere. Okay? They're the exact same thickness, but this oceanic lithosphere is denser on average, so it floats a little bit lower, essentially has a smaller percentage floating above the freeboard compared to the continental lithosphere, which has a higher percentage floating above freeboard. So the bottom line is that the height at which a block floats can be controlled by both its density and its thickness. Okay, so when we think about height above the freeboard, we have to think about density and thickness. Okay, so let's move into these calculations. How do we actually estimate the elevation of a floating lithospheric block? And this seems abstract right now, but I'll emphasize this is really important because the elevation of this floating block, that's where we live, right? That's Vermont or that's Tibet. And so if we want to think about how continents behave over time in terms of uplift and erosion, it helps to be able to actually make some quantitative estimates of elevation of these lithospheric blocks. So a major problem with computing the elevation of a lithospheric block is that we need a reference frame. We need to ask its elevation with respect to what? And in all these cartoons we've been drawing, we've been showing the lithospheric blocks as floating in this kind of hypothetical top of the asthenosphere, as if they were blocks floating in water. but in fact, this specific reference frame doesn't really exist, or if it does, we don't know how to define it. So instead, it's more useful for us to define the height or the elevation of a lithospheric block in terms of its elevation relative to sea level, which is the reference frame we're used to using as humans, as in meters above sea level. So the full solution to doing this is to basically compare an unknown lithospheric block with another lithospheric block of a known elevation. And if you can balance those two blocks against each other, and one of them has a known surface elevation, then you can just compute the offset between the tops of the two blocks, and you've got the surface elevation of your unknown block. In this video, we're going to use a little bit of a simplified solution. And what we're going to do is we're going to assume this hypothetical top of the atmosphere is at a fixed depth below sea level. Okay, so we're going to assume we know this distance between sea level and the top of the atmosphere. And then we're essentially going to show you how to compute the depth of the block below the top of the atmosphere. And then at the very end, we'll just add on this little offset to get the depth of the block below sea level. So to compute the depth of the block, we're going to set up a force balance. And this force balance arises from the recognition that the lithospheric block is floating in the asthenosphere. And for any body that is floating in a liquid, there's a fundamental force balance between the force of the floating object, in this case a boat, that's exerting a force downward, and the force pushing back, which is the force of this displaced fluid right here. So all that water that's being pushed aside is actually exerting a force equal and opposite to the force of the boat, okay? And that force balance can be defined like this, where the force of the lithospheric block is equal to the force of the displaced asthenosphere. And those forces can be broken down into mass times acceleration, okay? So in this case, we've got the mass of the displaced asthenosphere times acceleration, and the mass of the displaced lithosphere times acceleration. So we'll bring that mass balance through our next slide here. It's the same as the previous one. And now we're going to just recognize that the acceleration term is a constant, and it actually cancels out of this equation. So we're essentially left with a mass balance, which is mass of the displaced asthenosphere is equal to the mass of the displaced lithosphere. Now, in general, we can break out mass and recognize that it's equal to density times volume, just in general, okay? And that volume, in turn, is equal to area times height, okay? So mass equals density times area times height. So if we know these three things, density, area, height, we can then compute a mass balance for our lithospheric block. And it's going to look just like this. Volume of asthenosphere times density of asthenosphere equals volume of lithosphere times density of lithosphere. Keeping in mind, this volume of asthenosphere represents the material displaced by this block, okay? So density is a little bit complicated to calculate. Although we're talking about lithospheric blocks, we need to always remember that the lithosphere is divided into two parts, the crust and the lithospheric mantle. And those have very different densities. For example, oceanic crust has a density of about 2,700 kilogram per meter cubed, whereas lithospheric mantle has a density of about 3,400 kilogram per meter cubed. So to estimate the average density of this whole lithospheric block, we would need to take a weighted average, and that's given by the density of the lithospheric block is equal to the fraction of crust times the density of the crust plus the fraction of lithospheric mantle times the density of lithospheric mantle. So for example, in this case, we might have roughly 20% crust, so that would be a fraction of 0.2, and we may have 80% lithospheric mantle, so a fraction of 0.8. So in any weighted average, these fractions need to add up to 1, right? So now that we have our weighted average density, we can solve for the height or the depth of the block below the top of the asthenosphere. So we're going to start that solution with our mass balance here, just restate it again. And then we're going to do a little bit of algebra on this statement, and we're going to just solve it for the volume of the asthenosphere. And these are all things we know, our weighted average densities, our volumes. So we can solve for the total volume of this submerged area. Okay, that's V asthenosphere. And then once we know that, we can solve for this height simply by dividing the volume by an area of 1 meter squared. That's a little bit of a math trick, but essentially in this calculation it doesn't matter what the area is. The result is the same for any area, any sized block. And so we're just going to plug in an area of 1 meter squared here, and we're going to turn this volume right into a height or a depth below the top of the asthenosphere. All right, so now we know how deep the base of this block is below the top of the asthenosphere, but what we might be more interested in is how deep it is below sea level. So we'll do a final step here, and that's essentially to recognize that this term, the height below sea level, HBSL, is simply equal to the height of the asthenosphere plus this term, which is the offset between the sea level and the hypothetical top of the asthenosphere. So mathematically it just says that the depth below sea level is equal to the depth below the top of the asthenosphere plus the offset between the sea level and the asthenosphere. And of course this number would now give us the elevation of this block below sea level. If we want to know the elevation of the top of the block below sea level, we just need to do a little more math, taking into account the thickness of this block, right? So in summary, simple models predict that lithospheric blocks should be in isostatic equilibrium over long time scales. And calculating the depth of those blocks or the elevation of their surfaces below or above sea level can be helpful for all kinds of applications. And we can do that using a force balance that we just went through. And we did that in 2 steps. We essentially estimated the depth of the lithospheric block below the top of the asthenosphere first, and then we added on the offset to get the depth of the block below sea level. So I'll leave you with this concept question. You may need to watch the video a second time to get it, and we'll be using these concepts heavily in class and in the homework. Thanks, everybody.